Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, Electronic Configuration, Part 2. Material in this lecture builds upon the previous lecture, Electronic Configuration, Part 1. This lecture is a follow-up to the Electronic Configuration, Part 1 lecture. The expectation is that the student has already reviewed the basic process for determining the electronic configurations of an atom, and is ready to expand on that understanding and practice moving into and out of electronic configurations. Our first topic is a look at the exceptions to the general process for generating electronic configurations, or EC. The second topic has us expanding the process to get the electronic configurations of an ion. And finally, we will review the whole process of getting ECs with a quiz that focuses on finding the EC of an atom and, conversely, finding the atom type from an EC. As noted in the Electronic Configuration Part 1 lecture, this lecture covers the topic in depth, which may be significantly more than is covered in your class. Be aware of the level of understanding that is expected of you and view this lecture accordingly. Oh, and make sure you have a copy of the periodic table handy. A quick look at the table containing the first 18 elements, listed by atomic number, can help us reinforce the process of producing EC. Looking at the last orbital in the configuration, 1s gets filled. Then 2s, followed by the 6 elements that fill out the 2p, back to 2 elements for the 3s, and finally the 6 elements that fill out the 3p. The electronic configurations of noble gas are used as shorthand abbreviations. Exceptions to the EC rule are usually not a major concern in most chemistry courses. We will cover it for those students who will need some familiarity with the subject. Even so, the follow-up slide to this one, the one using the periodic table, establishes an acceptable level of understanding for this topic. Here we cover the underlying reasoning. Consider what should be the electronic configuration for copper with its 29 protons and electrons. The 29th electron, colored red here, is paired in the 4th of the 5 3d orbitals. The 5th orbital is occupied but unpaired. As can be seen using the stratified energy level diagram, the higher the energy level, the smaller the energy difference is between neighboring levels. They get closer together, which means generating a half-filled or fully filled set of orbitals sometimes involves promoting an electron from an orbital that is just a little lower in energy. That comes out of the complicated orbital mathematics. For copper, a survey of this electronic configuration shows it to have 9 electrons in its 3d orbitals. It is 1 electron short of having 10 electrons and filling its 3d orbitals. What it does is take one of the 4s electrons and moves it into the last of the 3d orbitals, thereby completing the set of 3d orbitals. Yes, there is now an unfilled 4s orbital, but it is half-filled, and the math says this is a more acceptable arrangement. There are some repairs we need to do to this EC. The 4s orbital is no longer 4s2. It is 4s1. And the 3d9 is now 3d10. That is an exception to the rule. For most students, a recognition of where the exceptions occur will be a sufficient understanding. The first of the 2 regions is where adding an electron completes a half-filled set of d orbitals. And that is where the last occupied orbital of an EC should have been Nd4. Promotion of electron from the preceding s orbital has Nd4 becoming Nd5. That is, each of the 5d orbitals having 1 electron, half-filled. For example, 3d4 or 4d4, which is chromium and molybdenum. In both cases, a lower energy s orbital electron has been promoted to a d orbital, yielding a d5. The other region is where adding electron or electrons completes the full set of d orbitals, and that is where the last occupied orbital is ND9. ND9 goes to ND10 with the promotion of electron from the preceding s orbital. Examples include copper, silver, and palladium. Palladium is a good trick question on a test because it looks like it should end in 4d8, but both 5s electrons are promoted to make 4d8 into 4d10. That's really a sufficient look at exceptions. The other topic of the lecture is electronic configurations of ions. An ion is an atom that has gained or lost one or more electrons. Elements coming right after a noble gas tend to lose electrons, becoming cations. These include the 1A or column 1 alkali metals and the 2A or column 2 alkaline earth metals. Elements coming right before a noble gas tend to gain electrons, becoming anions. These include the 6A main group or column 16 elements and the 7A or column 17 halogens. Since ions by their very definition have different number of electrons than the corresponding atom, they must have different ECs. To get an electronic configuration, use the atom's EC and then add or subtract the gained or lost electron or electrons. A useful tip is that ion electronic configurations tend to be the same as that of their nearest noble gas. A table comparing an atom's EC with its corresponding ion's EC will show us what ions an element tends to if its motivation is to achieve a noble gas electronic configuration. We will limit ourselves only to the most common ion for each element. Noble gases on this table include neon and argon. Their ECs both end in full filled sets of p orbitals. We will take a look at a few elements, starting with the one that is in a category all by itself, hydrogen. It only has one electron, and if it loses that, it is just a positively charged ion. It's just a proton. It has no EC. Hopping down to oxygen, if oxygen gains 2 negatively charged electrons, thereby adopting a -2 charge, it will, in effect, be adding electrons to the 2p orbitals, making the ion electronic configuration end in 2p6. 4 plus 2 equals 6. 2p6, just like neon. The atomic EC of fluorine ends in 2p5. If fluorine gains 1 electron, thereby adopting a negative charge, the ion electronic configuration will also gain 1 electron, and 2p5 will become 2p6. Right, the same as neon. Moving to the other side of neon, sodium has an EC that ends in 3s1. If sodium loses 1 electron, it will have 1 more positively charged proton than electrons and adopt a +1 charge. Removing the 1 electron from the 3s orbital will leave the 3s as unoccupied. As such, it will not be included in the ion EC, which will now end in 2p6. Yep, another neon-like configuration. A similar argument can be made for magnesium. Its last occupied orbital is 3s2. If it loses 2 electrons from its 3s orbital, it will have 2 more protons than electrons and adopt a +2 charge, and have an ionic EC that does not include the 3s orbital. It will have a neon-like electronic configuration. Once again, the ionic configuration tends to be the same as that of a noble gas. We could make the same set of arguments for the elements right before and right after argon on the periodic table. Before they gain electrons until they have an argon EC, and after they lose until they have an argon EC. So, if the student is comfortable generating ECs for atoms, then coming up with an EC of a corresponding ion should not be that difficult, because ion electronic configuration tend to be the same as that of a noble gas. Material in this lecture readily lends itself to quizzing. See where you stand on electronic configuration by stopping the lecture after each question and finding the answer on your own. A review of the answer will still follow. Given the EC, 1s2, 2s2, 2p6, 3s1, find the element. The key to determining what element or atom the EC represents is in the last orbital of the EC. By inspection, we see that that is the 3s orbital. We need to find that orbital on the table. 1s2, 2s2, 2p2, 3s. Our element is in this row. The other piece of information is in the superscript of the last orbital in the EC, and that is a 1. One element into the 3s orbital is sodium. We could also have counted the electrons in the EC and come up with the number of electrons in the atom. Since atoms have the same number of electrons as protons, we can use the electronic count as the atomic number. Let's try it. Just add the superscripts. 2 plus 2 plus 6 plus 1 equals 11. And 11 protons is the element sodium. On to our second question. Given the element P, find the electronic configuration. We will answer this question two ways. The first is using the stratified energy level diagram. The second, and probably the most useful, is on the periodic table. Phosphorus has 15 protons and electrons. The first pair go in the 1s, the second pair in the 2s, the next 6 go into the 2p, and the next 2 go into the 3s. Of the remaining 3 electrons, 1 goes into each of the 3p orbitals. No pairing because the 3p orbitals are all equal energy orbitals. 1s2, 2s2, 2p6, 3s2, 3p3, or brackets neon 3s2, 3p3. Getting an EC from the periodic table is essentially the same thing. To give us a point to shoot at, locate phosphorus on the table. When the student can identify that phosphorus is the third element over in the 3p block, they will have recognized that the EC will end in 3p3 and have demonstrated command of this topic. Regardless of one's skills at determining orbital blocks, it should be clear from the atomic number that phosphorus has 15 protons and therefore 15 electrons. Let's move through the orbitals, starting at the lowest energy orbital, 1s, up to the top and on the left, and assign the 15 electrons to them using the Aufbau principle and Hund rule. 1s2, 2s2, 2p6, 3s2, leaving 3 electrons to go into the 3p orbital. And since the written form of the EC does not explicitly specify how those last 3 electrons are distributed, we are not required to include that information. While using the periodic table may be quicker and easier for generating ECs, it lacks the detail of the stratified energy level diagram. And that's 2 down. Let's try a slightly harder one. Given this longer, more complicated EC, find which element it represents. Now, this longer EC may seem a bit more intimidating, but like the previous problem, using sodium's EC, it is solved using just the information in the last listed orbital, 3d2. We can find the 3d orbital by walking our way across the periodic table and calling out the orbitals block by block, or we can refer to this process of listing just the blocks of the orbitals where they first appear. That is 1s for the s orbital, 2p for the p orbital, and 3d for the d orbitals. Our element is in this row. That leaves the information in the superscript to give us a count of how many elements to count over from the start of the block. Yep, 2. Giving us the element 22, titanium. Another even simpler approach to solving this problem is to add all the superscript numbers together. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 2. It also comes up to 22, the atomic number of titanium. And now we have a way to double check our answer. Our fourth problem, we shall try to find another EC. This time it's for iron, Fe. Since this is the first time we're attempting an EC of an element containing d orbitals, we should solve the problem using both the stratified diagram and the periodic table. Iron has 26 protons and 26 electrons. The first 2 go in the 1s, then 2 in the 2s, 6 in the 2p, 2 more in the 3s, 6 in the 3p, 2 more in the 4s, leaving us with 6 more electrons to go into the 3d orbitals. D orbitals are filled in the same manner as the p orbitals. We use the same principle of filling all equal energy orbitals before pairing. So we add 1 electron to each of the 5 d orbitals. 1, 2, 3, 4, and 5. Leaving a last electron to pair with the first of the 3d orbitals. As mentioned earlier, there is really no ranking between equal energy orbitals, but the general practice is to fill left to right. The EC is therefore 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Note that once we move into the 3d orbitals, the listing of the orbitals in the EC does not follow the order on the diagram. To make the written format easier to read, most textbooks group energy levels by their principal energy number. Here, all the n equals 3 orbitals are grouped together. That will hold for all the larger n levels too. The most previous noble gas to iron is argon. We can use the argon shortcut to simplify the electronic configuration. After covering this material in class, students will generally not use the stratified diagram. They should instead rely on understanding of EC as viewed with the periodic table. This method begins with locating the element iron. It is element 26. If we can, we should identify that it resides in the 3D block and that it is the 6th element of that block. This allows us to write the last orbital in the EC. We can finish the EC by listing those filled orbitals in order from lowest energy orbital, top left, to highest occupied energy orbital, 3D. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and as found earlier, 3d6. Let's not forget to group by energy level. That means moving the 3d6 before the 4s2. We can use the noble gas shortcut by noting that argon is the noble gas preceding iron. These questions are the most common quiz and exam questions covering the electronic configurations. The only other major type that can come up, and it's instructor dependent, is one that asks the students to get the EC from the stratified relative energy diagram. Well, first of all, we should find the last occupied orbital, which will give us an ending point. It is the 4s orbital, and it has just 1 electron in it. Now we know that the electronic configuration ends in 4s1. For the rest of the EC, we read from bottom up and note the number of electrons. And that should be a maximum for all the orbitals below 4s. 1s2, 2s2, 2p6, 3s2, 3p6. And that leaves the half-filled 4s orbital, 4s1. But what element does it represent? Again, we seek the last listed orbital, 4s1. Where is the first element in the 4s block? Where is the 4s block? We can walk our way there by going down the periodic table and across, or we can note where 1s is and drop down the block, increasing n by 1. 2s, 3s, and then 4s. What is the first element of the 4s block? K. Potassium. And that completes the quiz. Let's recap the lecture. For a review of the basics of the assignment of an atom's electronic configuration, see the Electronic Configuration Part 1 lecture. This lecture looked at the exceptions to the Aufbau principle. They mainly occur at the promotion of an electron or two from a lower energy orbital in order to fill or half-fill a higher orbital. The benefit of filling or half-filling the d orbitals compensates for promoting an electron from a lower energy orbital. This generally occurs where we expect to be adding the last electron at Nd9 or Nd4. Nd9 gets promoted to Nd10 and Nd4 gets promoted to Nd5. Then there's ion electronic configuration. Use the atoms EC, then add or subtract the gained or lost electron or electrons. Ions tend to have the same EC as that of a noble gas. And that concludes our lecture. Make these new ideas an asset with a little practice.